Okay, so today we'll discuss voltage divider. First, let's start with some basics about the relationship between the voltage and resistance of a circuit. Voltage is proportional to resistance. V is proportional to R. We know from the Ohm's law that I is equal to V over R, and then V is equal to IR. Now see this V and R, they are in a proportional position. Let's explain this with some numbers. If we put some numbers, let's say I is equal to 5 amperes and R is equal to 2 ohms. Okay, so what will V be? V is equal to IR, right? V is equal to 5 times 2 is equal to 10 volts. Now if we keep the current constant, so I will stay 5, I does not change, but we change the resistance. Let's say we increase the resistance, so we have 5, and now for R we put R prime is equal to 5 ohms. Okay, so we increase the resistance to 5 ohm. Now what is the voltage? The voltage is now 25 volts. So we can see that when current is kept the same but resistance is increased, then voltage also increases. So this means that voltage is proportional to resistance throughout the circuit, and there's a ratio rule for the proportionality of voltage and resistance, which states that the ratio of voltages, so multiple voltages across series resistors. Again, notice this is an important part. Series resistors, we'll see why it's an important part. So the ratio of voltages across series resistors is in direct proportion to the ratio of their resistive values. Now this statement is also expressed with an equation like this: V1 over V2 is equal to R1 over R2. Now you can also rearrange this and write V1 over R1 is equal to V2 over R2. This is actually how I keep it in mind. It's easier for me, like V1 over R1 and 2 over R2. Anyways, you can memorize it however you want. Now let's move on to the voltage divider law. So in voltage divider, this comes from the Ohm's law. Okay, so I is equal to V over R, and so V is equal to IR. Now Vx means the voltage of any resistor in the circuit, or any load in the circuit, and then Rx means the resistance of that specific load. So from this we can find the resistance of any specific load. And again, from the ratio equation that we had, so V1 over R1 is equal to V2 over R2. V2 over R2. From this we can derive Vx. So Vx is equal to E over RT, so our total, times Rx. So this will be V2. Now there's a V2 is E, which means the total voltage of the circuit. R2 is RT, so the total resistance of the circuit, of the series circuit. Again, remember this, the voltage across series resistors. This is an important part, like I said. Again, notice here, this RT will be the total resistance of the series circuit, and times Rx, the resistance of that individual load that we are measuring the voltage of, we are calculating the voltage of. So this is the voltage divider rule. Let me write that in red. So Vx is equal to E over RT times Rx. Again, remember, RT is the total resistance of the series circuit. Now why series circuit? Let's explain that. In a parallel circuit, the voltage is the same throughout all the resistors or all the loads. So if we have a mixed circuit where some resistors are in a parallel connection, all those resistors in a parallel connection will have the same voltage, but the resistors in series connection will have different voltage. So if we want to find the specific if we want to find the individual voltage for a resistor in a parallel circuit, that is the same as the total voltage of the parallel circuit. But if we want to find the individual resistance of a resistor in a series circuit, then we use this voltage divider rule, where this RT is the total resistance of the series circuit, of the series connection of the circuit. Okay, and this is an important point. The sum of each individual voltage will always be equal to the provided electromotive force. Now again, this is applicable only for series connections. So if we have two series resistors, each and the total voltage is, let's just draw a circuit. So if we have a circuit where the total voltage is, let's say, 10 volts, and we have two series resistors, okay, then the voltage of each resistor will be 5 volt and 5 volt. So the sum of all the individual voltages in a circuit, in a series circuit, will be equal to the total voltage. Now let's move on to some practice questions. So this is a series circuit. Again, how do we know it's a series circuit? From the previous video explaining series circuits, we have a single common point between two resistors, so that means a series circuit. Now our 5 ohm, 10 ohm, 3 ohm. Now we have to find VR3. VR3 means the voltage across the R3 resistor. Now how do we find that? From the voltage divider rule, we have, remember this rule, Vx equal to E over RT. Let's just write that here. So Vx is equal to E over RT times Rx. Now what is X here? X is 3. So we will rewrite it as V3 is equal to E, which is total, so 30 volts. RT, again, this is the whole thing is series circuit. So RT is the total resistance of the whole thing. So that's 5 plus 10, 15 plus 3, 18. So 18 ohms times Rx. Now again, Rx, X means 3, so R3. That means 3 ohms. Right? So what do we have there? 30 over 18 times 3. So that's 5 volts. Okay. So VR3 here will be 5 volts. Now let's verify this part, where the sum of each individual voltage will always be equal to the provided electromotive force. Is that true? Let's find the voltage of R2. So R2 will be VR2 is equal to, again, E over, so 30 volts over total resistance, which is 18 here. 18 times R2, that is 10, is equal to 30 over 18 times 2. 30 over 18 times 10. So that's 16.67. 16.67 volts. Again, VR1. So VR1 would be 30 over total, so 18 times R1, so 5. And that is 30 over 18 times 5. 8.33. 8.33 volts. Now let's see what total voltage we calculate. So we calculated V3 is equal to 5 volts plus VR2 is equal to 16.67 volts plus VR1 is equal to 8.33 volts. 8.33 is equal to 5 plus 16.67 plus 8.33. That's 30 volts, exactly as our given electromotive force. So we have verified that this statement is indeed true. The sum of each individual voltage will always be equal to the provided electromotive force. But again, this is only applicable for series circuits. Now let's do another practice question. This is a mixed circuit. We have parallel connections all over here, and then we have a series connection here. Now find the voltage in the 10 ohm resistor. So for the voltage in the 10 ohm resistor, the voltage across here, again we apply the voltage divider rule, which was Vx is equal to E over RT times Rx. Now what's X for us? It's 10. So V10 is equal to E, total voltage, so 30 volts. Now RT. What will RT be? Will it be the total resistance of the entire circuit? Actually no. It will be the total resistance of only this part. Why? Because the total resistance here is the total resistance of the series connection. All of this, let me draw it with another color. So all of this is in parallel connection. Here two common points. So these are all in parallel connection. So in RT, for the voltage divider, all these parallel connection resistance do not matter. Only the series connection here matters. So the series connection here has 2 ohms and 10 ohms. So the total resistance would be 2 plus 10, 12 ohms, times Rx, which is R10, which is 10 ohms. So what's our total resistance? Our voltage for the 10 ohm resistor? 30 over 12 times 10. So that's 25 volts. Now again, let's verify this statement, that the sum of each individual voltage will always be equal to the provided electromotive force. Now this is a different scenario because we have a lot of resistors. But again, remember that statement was only applicable for the series connections. So here in the series connection we have two resistors, 10 ohm and 2 ohm. For 10 ohm we have calculated 25 volts. So 2 ohm should be 5 volts because 30 minus 25 is 5. Let's see if that's true. So V2 will be 2 means V2 ohm is equal to, so 30 over the total of the series part, so 12 times this 2 ohm resistor, so 2, that is 30 over 12 times 2, 5 volts. So exactly as we expected. Now 25 plus 5 is equal to 30 volts, the same as the electromotive force. So that statement is true for series connections, even when there are parallel connections in the circuit. Now let's do this one. So this is a parallel circuit, right? R1, R2 and R3 all are in parallel connections. Here two common points. So it's a completely parallel circuit. Now we have to find VR2. So the voltage across this resistor. Now remember, from the parallel circuit lesson, the voltage across all resistors in a parallel circuit is the same. So VR1, VR2, VR3 will all be the same as the total voltage of the circuit, right? So do we have to use the voltage divider rule here? We don't. We can just find the total voltage. Again, we don't have to find the total voltage because it's given to us. E is equal to 27 volts. So this voltage across VR2 will be 27 volts. So what just happened? Okay, so 27 volts. Let's verify that using our voltage divider rule. So Vx is equal to E over RT times Rx. So now let's put the values. So VR2 is equal to, what's E? E is 27 volts over RT. Now see, RT, we cannot consider the total resistance of all the resistors here. Why? Because they are all in parallel connection, and we can only use the total resistance of the series connected resistors. Now there are no series resistors here, so for VR2 we can only use the resistance of R2 as total resistance, right? So 4 ohms times R2, so again 4 ohms. So we can easily see that 4 is cancelled, and VR2 will be 27 volts. Simple. So again, remember, for parallel connections, the voltage is same. So voltage divider is not needed for parallel connections. Again, that important point, RT here is the total resistance of the series connections. So even if we have parallel connections like we had here, for RT we will only use the total of the series part, so 10 plus 2, here 12, not the entire circuit.